Okay, so this is my first video for digital systems. So let's walk over week one's material, what was taught. So in the lecture notes, we kind of learned about, I'll do the lab separately, but this is just the lectures. So like inside the lecture, we were just learning about like, I don't know, digital systems, like how hardware works, how things are stored, like relatively that kind of thing. So essentially, we were first introduced to such a diagram. It's just kind of like a simplified version of a CPU. So here we have something like this. What we have is over here, we have the register. Over here, we have the program counter and several registers inside. And what it does is that it can read stuff from the ALU, and then the ALU can write back to the register. So we see these arrows over here. And on another side, we have controller, and inside we have instructions. And then by addresses, we can access things in the memory that are stored like this. So that's kind of what it is. And there's just a lot of definition in the front. So a state is held in the register. And over here, there's the program counter, which we write as PC. It's basically a specific register that keeps track of where we are in the code and the next instruction. And also inside the von Neumann architecture, both instructions and data are stored in the same memory, and CPU treats them kind of differently. So there is such a thing as instruction, which tells the controller what to do, and data is processed by the ALU. And by ALU, I mean ALU is this arithmetic logic unit. So that's what it stands for. And then I don't want to specifically dive into the operation yet. So let's just first talk about things on the front that I kind of noted down. So there's something called the Turing machine, which is kind of like a math model of computation. What it is essentially it's just a thought of like having a very long tape, infinitely long, that basically acts as the memory of used to store memory. And what we have is like there's a head, which is used to read, write, and move the tape and get information from that. And then there's a state register, and there's a finite table of instructions that tells it what to do. And the Turing is because it's on the tape, it's a sequential model. And then there's the von Neumann architecture, which uses RAM, which is basically stands for random access memory, and it goes by addresses. That's kind of what I got from that. It's kind of just like a basic understanding of what we're diving into, and just a lot of vocabs. So in terms of specific operations that a CPU can do, there's the fetch, which is basically the controller looks at the PC with an address, and then it gets back that instruction. Decode, which is basically the controller reads the binary code to figure out the action, and then that's what it does. And the RISC is just stands for Reduced Instruction Set Computer. So it basically just loads data to the register, performs an action, then stores it back to the memory. Because over here we see that the ALU doesn't have a way straight to the memory. It has to go through the controller before. It has to go to the register, then the register to the controller, then accessing the memory. Like it can't directly link to the memory. And the action is like where ALU does the computation, it calculates stuff, and then the program counter updates to the new address. And then basically that's the process is repeated, and that's how the CPU functions. And essentially, it's not a magical process. Basically, how this works physically is we use voltage. So, like a high is just a one, so the voltage is relatively high. A low is when the voltage is low. So that's when it's near zero. And we just detect the change to see if anything changed. And then in the computer, all of the registers are 32-bit wide. So they basically are registers are used to hold the state of the CPU. And there's usually this many CPUs which are used. R0 to R7 are general purpose registers, so they can be used by any, and they're the most frequently used. And then we have R0 to R3 specifically handled differently during subroutine calls. So the result is returned in R0. And then they're usually overwritten. So then that's why we um, usually store it in R4 to R7 to be safe. And then R8 to R12 are high registers. So they are less used, but they're there. And then some of the more common ones that we also use for other functions are R15, or also known as the program counter that we have been talking about. This one stores the memory address of the next instruction. And then we have R14, which stands for the link register. So it's basically to store the return address whenever I call a subroutine. And this link register is really special. Not going to dive into why it is the case right now, but later on, yeah, we'll definitely talk about it. R13 is a stack pointer, which points to the top of a stack of local variables. So basically, that's what it does. And then the stack, as you increase stuff, add things to the local memory, you move the stack pointer lower. It's actually counterintuitive. When you add stuff, it goes down in memory. So that's how it works. And when you pop stuff, it goes back up, sort of like that. And then there's a PSR, which is processor status register. This stores the status flags. So it knows if the statement knows to jump or stay. And we often use these flags for like the if conditions, right? So we have four flags in particular, N, Z, C, V. N stands for negative, Z stands for zero, C equals carry, and V equals overflow. N basically just checks if the result is negative. Z checks if the result is equal to zero. Carry flag is basically checking if the unsigned exceeded the limit and is no longer true. And then the V is overflow, which is when it's signed, like it exceeded that limit. So it's when it's wrong. So then this is a guess an example of things. Instruction is in address 192. We have PC as in 192. Input R0, R1. Yeah, we have this flag 1010 from previous operation. Okay, yeah, so like this is our flag. This basically means the value of NZCV respectively. So then at this we have something like this is 0x. This means like the hexadecimal. This in the front is just hexadecimal, and our code is like the 1840. And then CPU basically fetches data at 192. The value is the hex 1840. And then we can just rewrite 1840 in terms of binary. And we get 1 is this, 8 is this, 4 is this, 0 is this. And then we see that the first few bits is the adds instruction. The next bit tells me that it's R1, the next three bits tell me it's R0, the next three bits tell me it's R0. So what in assembly this code basically means is adds R1, R0, R0. And S is basically means that I'm just updating the flags as I go. So what this means is that I want to add R1 and add the value in R0 into R1 and then put the result in R0, updating the status flag. So that's pretty straightforward, I say. And then we can have another example PC of this, and then that would be the result. We see that the result is 57, 34 remains the same from before, and that's kind of it. And then PC is increased by 2 because every address is a single byte, which is 8 bits. And then this thing over here has 4 digits, which times 4 bits is 16 bits. So this instruction takes up 2 bytes. So that's why our thing increases by 2. And this basically follows the ARM thumb rule, which you use to program our microbit. So it's kind of important. And there's also other things like that are 4 bytes and 8 bytes, depending on what we use. But we usually stick to the thumb one. So that's why we use 2. Um, and assembly language was basically uh, this kind of thing that I wrote up here. This is what assembly code looks like that we're expected to write. It's basically like a first level of abstraction from binary machine code. So it's like tiny bits of syntactic sugar. And the assembler is basically the program that translates this assembly to machine code that actually gets run. And then inside here we have bit allocation. So we actually can there are many limitations to what we can do versus what we can't. So for instance here, this operation adds R0, R1, 3 is legit because it's a 16-bit instruction, everything checks out. Um, this thing adds R0, R0, 10. This one works as well because it just works. Whereas this one, R0, R1, 10, fails. Why is that the case? Because 10 is too big and we have two registers here. We can think of it as like the assembly having opcode, destination, source, and then this is like the immediate number to add. What happens is that in the first instruction adds of that, we have the opcode desk register, source register, and then the immediate. The immediate only had inside here because the way it's programmed, there's only 3 bits left. So then the maximum value is 7. So that's why when we add 10 here, it fails. Whereas in the thing case of like R0, R010, it's designed so that it's the same register. So then there's actually 8 bits allocated. So that's why the 10 over there is okay because we're within the 255 limit. So that's kind of like basically watching out for how much bits is actually allocated to each instruction, right? And making sure that you don't exceed that limit. So there's a lot of quirks, which are basically trade-off between flexibility and size. Um, yeah. And over here, just a small note is that like the X basically means hexadecimal if it begins with that, and if it begins with B, it basically means it's in binary. So for instance, here, this one just means that 4770 is in hexadecimal. So then when I have such an instruction, I can convert it back. Like 4770, I can write it as like in terms of binary, I split each one and I can figure out what it means. Okay, cool. Moving on. Some useful things to know is BX. BX basically means branch and exchange. So it's just like a jump. That's kind of what it is. Like pretty straightforward. And the RM here is like a placeholder or a variable. So then when we set the program counter to RM, it basically takes address stored in RM and overwrites the PC with that value. So then once that PC is overwritten, CPU basically jumps to that new address. And then the next thing is like this over here is 14 in register 14. We know that it's the link register. So when we do BXLR, this is basically equivalent to our return statement because we use this at the end of a subroutine, which is basically quote unquote our function that we call. Um, that's the idea is that before we store the return, like where we were inside the thing, and then now when the sub function is called, then when we're done, we want to return back to where we were, right? Go out of this function. So then that's where we use BXLR. So that's like the return statement. So we're back at where we were. This is not used to call another function for sure. Um, yeah, copies of address are stored in LR to PC. Yeah, that makes sense. So then here we have PC is equal to 194, link register is 661, memory is at this. When we do BXLR, basically this jumps back to 660 and then the link register stays the same. Obviously, you might have caught on that 661 doesn't equal 660. This is because the memory address is always even in increments by 2. One is just the flag for thumb mode. So yeah. And then here we have ARM instructions. So that was what I was talking about earlier. Like thumb instructions are 16 bits, native are 32 bits. Thumb 2 is 16 to 32 mixed, which is kind of weird. But most of the time we do use thumb for the microbit. So that's pretty good to get familiar with. And then reusable code we kind of write up as subroutines, which are just functions as we know it. And now what we do is we store the returning address in the link register, jump to PC, run subroutine, and then return by BXLR. So that's pretty straightforward. And we need to assume that, like, because of the protocol of how it's designed and agreed upon, that subroutine will overwrite register 0 to 0, R3. So then that's why we store the values before calling it into other registers from 4 to 7 usually. Okay, that brings us to the end of the first chapter. I think it's relatively straightforward. It's just like an introduction of some new vocabulary and ideas. Let's end off here.